Hey kids, welcome to Unit 2. Can you believe that when I went to Walgreens and I was looking for some soda that I found this brand? Look, it says IB Pre-Cal on it. Unit 2, Polynomial and Rational Functions. So hopefully you recognize this as something that we studied in AAF. You had a polynomial unit, and then we also had a rational functions unit. Here we're going to combine those two, right? So we're going to go through some old topics, go through it pretty fast and a little bit more in depth, while at the same time adding some new ones. All right, so polynomial functions of higher degree. Now remember, the most famous polynomials on purpose are y equals x to the first, right? And f of x is equal to x squared. You should have spent a lot of time in Algebra 1 studying x to the first, lines, linear functions, and quadratic functions, because all the other polynomial functions are built from these, right? So that's why you need to study them in Algebra 1. Then you take a little bit of a break and you do geometry, and then you come back into Algebra 1 and you do more with lines and quadratics. And then you start to go to higher degree. So we are going to talk about all things that we did last year with higher degree polynomials and behavior. We're just going to formalize that, right? We're now going to introduce our limit language with end behavior. Zeros, right? We talked about zeros last year, zeros of polynomial functions and how to find them. We're going to introduce this idea of multiplicity of zeros, though. We didn't highlight that last year. And then the shape of our polynomials, right? We did talk about that last year. So first, I thought this was cute, right? Can you figure out what I'm saying here? So unfortunately, I have some stuff written on top of it, right? Polynomial. Right? Is that like Pac-Man eating the nom. All right. End behavior of polynomials. Old news. Polynomials, right? This looks scary. Pull this out at parties. It's so impressive. People are like, oh my God, you must be so smart. But all this is saying is that a polynomial function, right, is a function in terms of x where they can be arranged such that n is the highest degree that you see, right? And you can arrange it, right? It doesn't have to be, but you can arrange it so that the highest degree is first, and then your lower degrees go after it. Notice that this is, for instance, let's say n was 5, and then your next term was n to the 5 minus 1, and then it would be n to the third, n to the second, and then, x to the third, x to the second, and then x to the first. Technically, this is x to the 0, right? So the limits as x approaches positive and negative infinity. That means look at the n's. The end behavior are determined by the degree n, which by definition is the highest one you see in a polynomial. Even if it's not in the right order, it is the highest degree of all the terms of the polynomial, and the leading coefficient of that highest degree, right? A sub n, not a sub n minus 1. So a summarizer from last year, we talked about functions that behave like x to the first on the ends. On the ends, this looks like y equals x. This looks like y equals negative x. Not in the middle, but at the ends. At the ends, this function looks like, is not equal to, but looks like y equals x squared. And this one looks like, but is not, y equals negative x squares. On the ends, all polynomials either look linear or quadratic at the ends. They all do. So how do I formalize that? Well, if my leading coefficient is positive, that's what this says, leading coefficient positive, but the highest degree is odd, then the limit as you go to the far left goes down, right? The behavior as you go far left goes down, and the far right goes up. Conversely, if your leading coefficient is negative, if your leading coefficient is negative and your highest degree is all still odd, then on the left you go up, and on the right you go down. Right? I haven't done very good space management there, have I? However, if your leading coefficient is positive, right? And just look how fancy I can write all this, right? A sub n is greater than 0. That just means, is your leading coefficient positive and your highest degree is even, then on the left end you go up, and on the right end you go up. But if your leading coefficient is negative and your highest degree is even, then on the left and right you go down. Just what I circled on those graphs, that's what I say in fancy math language with limits. So when the directions say use limit notation to describe the end behavior, this is what they're after. This is what they mean. But in your head, you think far left go down, far right go up, because leading coefficient was positive, degree was odd. But you write it all this fancy way. So, end behavior of polynomials, continuity, and zeros. The nice thing about every single freaking polynomial, all polynomials are continuous. All of them. There's no breaks, no jumps, no holes in any polynomial. Polynomials also, I know something about their zeros or their possible numbers of zeros because I took AAF and I paid attention. Odd degree polynomials will have at least one real zero, right? If it behaves like a linear function on the ends, well then shoot, it's got to cross, right? If you have behavior, right? If you have opposite end behavior and you are continuous, and all polynomials are continuous, then you must hit the x-axis at least once. Real, right? Real x-axis is real numbers. So I'm not talking about non-real zeros. Even degree polynomials may not have any real zeros. So I want you to imagine this, right? This example right here, where this is an even degree polynomial because both ends go up. Imagine I picked this whole graph up and moved it way up here. Looks something like that. That even degree polynomial has 4 zeros, but none of them are real. And you are only expected to generate real solutions, real zeros, unless otherwise specified. Your default is all real numbers. And an x-axis only has real numbers on it. So an x-intercept is a real zero. That purple even degree polynomial has no real zeros, has no x-intercepts. But if you are an odd degree, you might have more. Like this one has 1, 2, 3, and it is an odd degree. This has 1, 2, 3, and it's odd degree, but it must have at least one, because no matter where I move this, let's say I shifted this one up. Doesn't look like it has x-intercepts, but hello, end behavior. That means that keeps going down, right? So if we were in person, I would be doing a little function dance for you, right? I know you're sad, right? That each one of these little figures, right, their arms kind of sort of represents a polynomial with, right? Oh, darn it. Like for, keep hitting the wrong, right? I don't care what's happening in the middle. Look at the arms, right? What's going on? Up, down. Odd degree, leading coefficient, positive. Down, down. Even degree, leading coefficient, negative, right? Up, down. Odd degree, leading coefficient, positive. Up, down. Odd degree, leading coefficient, positive. Up, up. Even degree, leading coefficient, positive. All because I don't care what happens in the middle. When I'm talking about end behavior, I only really have to think about lines, quadratics. So look at this example. Use limit notation. Pay attention to the direction. So in your notes, I've made it red. You should make it bold or underline or some other color, or highlight, whatever you want. But if the directions ask you to use a notation, there's going to be rubric points for that notation. Use limit notation to describe the end behavior of this. Now, this is a trap. You are not expected to multiply that out. Hello, that is not 15 to the 15th and negative x to the 15th. That is 15 minus x times 15 minus x times 15 minus x times 15 minus x, OMG. But because I just need the end behavior, I just need to know the highest degree on x, and I need to know the sign of the leading coefficient. Well, this is 15 minus x 15 times, right? So you're going to multiply a negative x times a negative x times a negative x times a negative x. I mean, you're going to be multiplying a lot of other stuff, but there's going to be a negative x 15 times. So I don't know exactly what is all in here after I multiply this out 15 times, but I do know that I'm going to end with, right, a bunch of terms and negative x to the 15th. That's odd, isn't it? So what is the highest degree that I see, that I would see if I multiplied it all out? 15. Therefore odd. Now I just need to think about the sign of my leading coefficient, and here's the trap. If you say the sign of the leading coefficient is negative, you've missed something. Aunt Sally matters. The order of operations says you have to take care of all of this. Then you're going to multiply everybody by a negative 15. So what happens when you have a negative x to the 15th that you distributed a negative 15 to? OMG. Therefore, what happens when you go far left? What happens when you go far right? Since this is an odd degree with a positive leading coefficient, on the left end you go down and on the right end you go up. Like a line, x to the first, positive x to the first. Notice that it's the same thinking, right? I'm doing the same thing here. They just have given me limit notation. So sometimes you're asked to demonstrate the fact that you can write in limit notation. Sometimes you're going to be asked to read limit notation. Evaluate the limit as x goes to negative infinity. That means what happens on the left end. Searching, searching, searching. Where's my highest degree? Ah, there it is. There's my highest degree. Even. What is the sign of the leading coefficient, right? I know it's not in the lead, but by definition, the leading coefficient is on the variable with the highest degree of a polynomial. Sign of that leading coefficient, is there anything multiplying it? No, no. So there's nothing out here I have to worry about, like the negative 15. So even, negative. What's happening on the left end is actually the same thing that's happening on the right end, isn't it? Going down. All right? So there's my thinking process for how I deal with end behavior. I don't care how many terms are in the middle. The middle terms have a huge effect on the middle of the graph. But the ends of the graph are determined by your highest degree, and because it's the most powerful, and the sign of the dilation factor on front of that. So for both of these problems, as soon as I knew end behavior, I was thinking, where's my x? What's the exponent on it? Then what's it being multiplied by? Same thing with the other one. It's an end behavior. Ignore everybody else. Where's my highest x? What's the coefficient on it? Right? So again, I should have put 2 right circles on this one because I did have to think about that. Look at the second problem. What if I had said, evaluate this limit, right? And I gave you a factored form. Is this entire expression, oh gosh darn it, is this entire expression now a 4th degree? Is that my highest degree anymore? No, it's not, because eventually I'm going to multiply negative 2x to the 4th times what? Another x to the 1st. So now my highest degree is 5, which is odd. The leading coefficient, right? There's a 1 on here, so when I multiply these, I still get a negative 2 in front. So my leading coefficient is negative. What happens on the left? If you have an odd degree and your leading coefficient is negative, you look like a line on the ends. Who cares what happens in the middle? You have on the ends, you look like a line with a negative leading coefficient. So what's happening on the left? You're going to positive infinity. All right, check this out. This is kind of sort of the IVT, right? Mixed with my end behavior discussion. Explain why. Now, hear me. Hear me with my thought process, not just what I'm writing, but what I'm saying. Why is it that this linear function with a positive leading coefficient will be the same somewhere? That's what it means to have a solution. Be the same somewhere. Cross, intersect this cubic function with a positive leading coefficient, right? You know what 12 plus 11x looks like. Looks like that. You kind of sort of know what x cubed with a leading coefficient looks like. Something like that. Look at their end behaviors. They're both polynomial. They're both continuous. They're going to be equal somewhere. It has to be so. because they both have odd degrees, so their end behaviors both go to positive infinity on one end and negative infinity to another, and they have to cross somewhere. What you also need to understand is the same question, because of algebra 1, here is the same exact question. That is the exact same question, because it is legal across an equal sign to move the 12 and the 11x over. So does this cubic function ever equal 0? Is the same thing as asking, does this x cubed plus 2x squared cubic function equal the linear function 12 plus 11x OMG? So I don't care how you think about it. That's the power of algebra. I can think about it either way, and I get the same answer. Yes, because of the end behavior, right? I know the end behavior. They must. Speaking of zeros, for a function, solutions, if you are equal to 0, we just call the solutions are called zeros. A solution just means one side of an equation is equal to another. Is there some value that makes one side of an equation equal to another? Well, if one side of the equation is 0, then the solutions are called zeros. Graphically, those are called x-intercepts. For the most part, we use x-intercept, zeros, and roots interchangeably. When we don't is when we expand our set from real numbers to the set of complex numbers, because some zeros of some polynomials are not real. But we are going to be dealing in the set of real numbers, therefore all of our zeros are x-intercepts. So finding the zeros of this cubic function, firstly, I know there's got to be at least one. This is, gosh darn it. This is a cubic function. All cubic functions have at least one. So I know I'm going to find at least one zero. Good F word. Factor. More factoring. And a pattern. That is really x times x minus 5 times x minus 5, right? This is just a more concise way to write it. But this is actually very useful for me when I'm thinking about zeros. There are 3 zeros. The 3 zeros here, what x's create 0? Well, if you put 0 in there, if x is equal to 0, this side will equal 0. If x is equal to 5 times 0 is 0. What can you put in place of this x? Hey, these two numbers are the same. We call that a repeated root. But it is very important to note that there are 3 factors. There are 3 factors. It's just that one of them happens to be repeated. X to the first and x squared gives me x cubed. So, with the knowledge I can get without a calculator, if you combine end behavior, the fact that all polynomials are continuous, the zeros and the y-intercept, I can make a reasonable sketch. It doesn't need to be crazy, but I can make a reasonable sketch of this graph, right? I know this graph has to hit the x-axis at 0 and at 5, but with a repeated root. I also know that since the leading coefficient is odd and my leading coefficient is positive, I know my ends have to look like that. A y-intercept just means plugging in 0 for x, and I got 0 cubed minus 10 times 0 squared plus 25 times 0, I got 0. So my y-intercept is also 0. So Because this function is continuous, I know I have to come up here through 0. I have to come down because I have to hit that 5. And then I can't go back down again because I don't have another x-intercept, so I have to turn around right here on the axis and swoosh back up. Right? That might be a terrible picture, but it's got the right end behavior, the right x and y intercepts, the right number of turning points. One turning point I call a cross, right? Or a hit. Right? My function hit and crosses. But notice here, this x-intercept was the result of the repeated factor, and I didn't cross. I just hit and left. Call this a kiss. Came down, kissed the x-axis and went right back up. Here, I came right running, just screaming right on through the x-axis, right? But here, I just came down, saw the x-axis, said, and left, okay? Here is another AAF objective. If I give you zeros, can you give me standard form of the cubic function back? So you learned last year what standard form was. And standard form just means I have no parentheses. Everything's multiplied out, which is highly annoying. Whoops. Oh, gosh darn it. I keep leaning across my tablet and it keeps like, right? And yes, this makes me cry because I know I'm not scared of multiplying it out, but I am annoyed, right? If I have these zeros, notice these zeros are real. They're just not nice, right? Square root of 2 is like 1.4-ish. So this is 1 plus 1.4 and this is 1 minus 1.4. Those are still real numbers, right? So those are my 3 factors. Notice that there is a dilation factor. They said hello. There is a dilation factor. I have left the assumption that my dilation factor is 1, but it doesn't have to be. I could make my dilation factor anything because they didn't tell me what it had to be. I think I'll be nice on myself and make it a 1. But I am going to have to annoyingly use some prerequisite knowledge to multiply that out quickly and get a quadratic, and then multiply that quadratic by this binomial. I'm not going to take this screen time to do that, but I will tell you what I end up with and then see if you can match it and check my work to make sure I did it right. Because again, this is an objective we did last year, but you are still responsible for. But the important part is knowing that factors get me zeros, zeros get me factors. And then from factored form, I can expand it into standard form if somebody makes me. Oh, that y-intercept. Y-intercepts are, right, anytime, any place, anywhere. How do you get a y-intercept? You plug in 0 for the independent variable. But let me tell you how many kids are tempted to multiply this all out to get the y-intercept. Please don't. Just replace t with 0. So what is that? 0 minus 3 is negative 3. 0 plus 1 is 1. 0 plus 2 is 2. 2 squared is 4. So this y-intercept is negative 12. And one of the cues that this should have been a very easy problem, I've told you this before, and I'll tell you many times again. When you see the words write down, it means there is 1 point available in the rubric, and it should be an obvious, easy thing to figure out, right? So if you find yourself doing an awful lot of work on a write down problem, you've missed something obvious. There it is. There is a picture of that graph. Now that obviously I got that from a calculator, but notice, and I had to change my scale. Look at my scale here. This is all the way to 200. So this number down here is a negative 12. But I knew that without the graph. Does this surprise you? I hope not, right? Here is a whole bunch of things that I can tell about this graph just by looking at factored form. The multiplicity of zeros. Some zeros over a function may be repeated. How you can tell is if x minus c, and c is just some domain number, raised to a number is a factor. How do you know you're a factor? Because you're multiplying. So look at what I have up there. C is called the zero with a multiplicity of the exponent. So up here in my polynomial P, I can already see that there is 0 at 3, right? Because 3 makes, right? To find the y-intercept, you plug in 0 for t, but to find x-intercept, you need to know what creates 0. How do I get 0 over here? Well, if t is equal to 3, I get 0. If t is equal to negative 1, I get 0. And if t is equal to negative 2, I get 0. But negative 2 is a repeated root. It's technically used twice. So we say that negative 2 is a 0 because it makes y 0 of multiplicity what? Multiplicity 2. I mean, technically, 3 is a 0 of multiplicity 1. Negative 1 is a 0 of multiplicity 1 because there's an exponent of 1 here, right? Negative 2, but we don't, right? That's so common, we don't really say it. It's just like saying x to the first. We don't really, we say just x, right? So multiplicity 1, we don't really talk about its multiplicity. But any factor that is repeated, we talk about the multiplicity. So negative 2 is a 0 with multiplicity 2. So here's some generalizations. If that multiplicity is odd, the function crosses it, hits the x-axis and goes right through. Bye-bye. But if m is even, the function touches the x-axis, pauses, gives it a little kiss, and then goes back. Goes back the same way, right? It touches the axis, mwah, but does not cross. So here, 3 is a 0 of multiplicity 1. The function just runs right through it. Bye-bye. Negative 1. The function just runs right through the x-intercept. Bye-bye. But at negative 2, whoops, that's a negative 12 down there, by the way. At negative 2, the function comes down. At negative 2, mwah, gives it a kiss at negative 2, goes back up before coming back down. Right? So notice the way that graph, it was kind of hard to see on that graph that there was that little wave there, but that wave has to be there because of the multiplicity. So look at all the things I can tell about this, this function P of t without a calculator. Without a calculator or a graphing program, I could tell that the degree was what? What was the degree here? It's not 2, right? T squared times t to the first times t to the first, the highest exponent you'll see when it gets multiplied out is 4. What's the leading coefficient? Well, this t gets squared multiplied by t multiplied times t. Oh, that's just going to be 1t to the 4th. So my leading coefficient is positive 1. What's the end behavior of a degree 4th polynomial with a positive leading coefficient? Like a quadratic on the ends with a leading coefficient. How about the zeros? Well, in fact, either I have to factor it or, thank goodness this was given to me in factored form. I'm looking for 4 possible zeros. And in factored form, I got 4 zeros, right? 3, -1, and -2 twice. Cross or kiss? 3 was a cross. -1 was a cross. But -2 was a kiss because it was multiplicity 2. Y-intercept, I just plugged in 0 for t, and I got -12. So because polynomials are continuous, I would have graphed without a calculator this shape. I would have graphed the y-intercept. I would have graphed the crossing x-intercept, the crossing x-intercept, and the kissing x-intercept. And I knew it had to kiss this way because the end behavior said you have to come down, kiss and go up, then turn around for the -1, get down there to -12 to hit the y-intercept, go down somewhere, I don't know exactly how far, but I got to come back up for this crossing x-intercept because I have to end up this way. Right? Really good idea of what the polynomial is doing with no electronic help. So let's practice that. Right? Notice I've given, here's another occasion where I've given you factored form. You're happy for factored form. If I don't give you factored form, you got to get to factored form. But that's why you took AAF. We taught you how to factor higher order polynomials, and we will review that next lesson as well. But I've given you factored form, so without a calculator, think about the continuity. Polynomial is always continuous. Multiplicity of zeros. How the zeros go to the x-intercepts. Also think about the y-intercept. And think about end behavior. So this is a polynomial. What degree? Right? What degree am I? Not second degree. X squared times what? X to the first means it's a degree 3, right? What's the leading coefficient? Positive x times positive x is positive 1x squared times positive 1x is going to give me positive 1x cubed. Therefore, what's the end behavior? Like a line with a positive leading coefficient. What's the y-intercept? Plug in 0. 0 minus 2 squared is 4 times 0 plus 1 is 1. 1 times 4 is 4. Zeros, I'm in factored form. What generates? What x or x's makes 0? Well, when you plug in -1 here, you get 0. This is multiplicity 1. So at -1, you are going to cross the x-axis. But you can also put 2 here. 2 minus 2 is 0. 0 times I don't care is 0. But this has multiplicity 2. So -1 is a cross, but 2 is a kiss. So put that all together. I've got to hit -1 and cross the x-axis. I got to come up and hit the y-intercept, but I got to get back down to the x-intercept of 2, stop and kiss, mwah, and then go back up to meet the end behavior. Right? It's not pretty, but it's a good, decent sketch with a lot of critical features. The only thing I don't know is the height of the max and mins. Don't forget, no polynomial is flat. None of them, right? There is no flat pieces, no matter what your calculator or computer is. Polynomial, and think about your number sense as to why that's not so, why that's so. No polynomial is flat, because remember, this, the line f of x is equal to 7, is a constant function up at a height of 7. But that's not a polynomial. That's a constant function, right? Yes, that's flat. But degree 1, 2, 3, 4, no other degree polynomial, right? I mean, some people will say, "Oh, that's a 0-degree polynomial." Okay, fine, right? First, second, third, fourth, fifth, none of them are flat anywhere. Also, if you are x to the first, that is the only polynomial that is straight. Every other polynomial has curvature, right? And we studied curvature last year, concave up and concave down. Nowhere, no polynomial past an x to the first is straight. None of them have sharp turns either. So when I did this turning point here, notice I made it rounded. I didn't come down here and hit right and make this a pointed sharp turn. No. That's not polynomial behavior. Polynomials are smooth, and except for x to the first, curvy, and never flat, unless you are an x to the 0, which you could argue is not a polynomial, or argue it is. I don't care. Don't make any of your other polynomials flat anywhere. All right, that is it. We will do a warm-up and some more practice of this in our live session. See you later.